All right, so we're going to move into chapter 2, which really starts looking at some really important definitions and looking at how we're going to use data and organize the data that we're starting to collect. The first thing, whenever you're looking at any kind of data, you want to ask yourself, is it credible? So is it good data? So when you're looking at, is data credible? A few questions you need to ask yourself. First one is the concept adequately reflected by the proposed measurements? So when they're measuring it, are they actually using correct measurements to measure? Are they doing correct data analysis and those type of things? So if they're looking at studying a vaccine, for example, are they studying it in a population? Are they studying it with the people who it should be studied on, or are they just studying it on healthy people? Like, those are the types of questions you need to ask. Is it measured accurately? So do they have a good way of collecting that data and organizing that data and analyzing that data? And did they collect enough of the data? So these are questions that, as we go through this class, you're going to get better understanding on how to do these things. I'm sure at some point in your education, you've learned the scientific method, either in your high school science classes or if you're taking a science class here. Statistics is done very similar. We're going to do the same kind of concept. We're going to gather information. We're going to come up with some kind of hypothesis that we're going to look at. We're going to test the hypothesis. And then we're going to use the data to support that hypothesis. If it supports it, then we can state that as a fact. If it doesn't support it, we go back. We change the data to figure out why it didn't support it. Was my hypothesis wrong originally, or did I collect inconclusive data, or do I need to do my experiment a little bit different? Just like when you're doing a scientific experiment, other people should be able to recreate your results. So when you're doing a study and using data, if somebody else does the same study, collect the data the same way, they should be able to replicate your results at the end. All right. One of the biggest things that can screw you up is what they call confounding variables. So these are things that they didn't take into account. So one of the examples that I gave you actually last class was we were talking about the effectiveness of the COVID vaccine and how in the studies it was very effective. It was like over 90% effective. But when they went public, it was down in the 70% effective. The confounding variables in that situation was how the person was acting outside of the vaccine. Were they social distancing? Were they using masking? Were they staying home and not going out? So those were those confounding variables that changed the actual data and skewed the results because they didn't take those into account. They didn't collect that data and that information to determine if that was causing the reason they didn't get COVID as compared to the vaccine. Does that make sense? So problem is that no matter what, when you're doing your studies, you're not going to be able to look at every possible variation of it unless you have a completely controlled experiment. When you're dealing with people, you do not have a completely controlled experiment. There's always going to be outside factors that are going to influence it. You're trying to minimize those as much as possible through your research and your data collection and your surveying and your studies, but you're always going to have some things that are going to influence it. And understanding what those things are and putting those in there so other people can use it and understand, well, this is what those type of confounding variables are, allows them to recreate that experiment later on. So this is the slightly varied of the scientific method. This is what we typically use in statistics. So you're going to clearly define the problem and any influential variables. Right, so notice we just talked about confounding variables. Influential variables are the variables that I'm going to be looking at. These are the things that could influence the actual outcome of my study. We're going to decide upon our objectives. It's just like your hypothesis. And we're going to, what are we going to use to determine our solution? So later on in the semester, we're going to look at how to actually use statistics to determine it. So in this case, you'd want to know how accurate you want your data. Do we want it with a 90% validity or 95% validity, or depending on the thing, do we have a 99% validity? Notice I never said 100. You can never be absolutely positively sure unless you talk to every single person. Okay, so you can get close, but you can't get exact. Create alternative solutions. So this is one of those things that is a lot harder for people to do. You know what your outcome you think it should be, but when you're doing this type of decision making, you want to come up with what's the alternate things. What are other things that could happen? Why do you think it'd be important to come up with those alternate solutions? Yeah.
Plan B, like another thing about, say, plan A doesn't work, then you can always transition to something else.
Okay. What's another reason? If I asked every single person in here an opinion, would I get the same opinion from everybody? No. So alternate solutions are things that you might not think of immediately. Okay? You have what you believe to be true, but when you're looking at the data, you want to have the ability to think outside of just your viewpoints. That's the biases we were talking about before. Everybody has them. So by looking at alternate solutions, you can start to minimize your bias because those are all the possible solutions that could be true. Okay. The next thing you want to look at is comparing those alternatives. So you've got yours, you looked at it, you've got your data. Now take those alternative solutions that you came up with and look at the data again with those alternative solutions in mind. Does it still work? Do those solutions make sense? If they do, then now we have a problem because now you might have multiple solutions that could work and they might not be the exact same thing. So this is where having multiple people looking at the study and doing it is important because you get multiple viewpoints. Next thing you want to look at is implement one of those chosen alternatives. So while you're implementing an alternative to what you did, what you think works, let's see if that works just as well, if not better, or if it acts worse. Because then you can say, well, mine works, and it works better than these other possible solutions that are out there. Okay, so this is where, when you think, I'm going to bring up COVID a lot because it was literally a data mine, like with how much stuff and everything else was around it. Because it was actually the first time in decades that we saw science happening and research happening in real time, where things constantly changed. And when people heard that change, because nobody had ever seen science work this way in the past, where you guys all take science classes, everything you were taught is basically a law. We all accept this is the way it works. Where we were seeing at this point where things were happening and changing because new data came out. And it's like, okay, well, this didn't work as well as we thought it was going to work, but we didn't have the data to be able to show that. And that frustrated people because people were not used to that. So, and this is where like this type of things comes in. It's like we looked at it, so okay, social distancing works. This is we're going to try. We shut everything down. We're going to social distance. We didn't know if it was going to work. We had no idea if it was going to work. We had no idea if the masks were going to work. We handed out all these masks. Didn't know if they were going to work. Some situations they helped, but it might not have solved the issue completely. People were still getting sick. So this is where we tried something. We experimented basically on the entire world at the same time and collected our data and said, okay, this didn't work, but this does. That's why when we started getting to August and September, when we started getting back to school year time, we were able to start going back to certain things because we had a general idea of how things worked. Okay, we knew that, well, if we did this, this, and this, we can minimize risk. Okay, we figured out that if we have 10 kids in a classroom, we could spread them out, that the concentration in the air was fine. We figured out that if we had airflow of a certain way, this would help minimize those risks, where we didn't know that back in April. So it was safer back in April to say, okay, close everything down, everybody home. Now, not everybody was happy with that, so that's why we had those options. That's why some of you literally did all your schooling at home for another year. For some of you are actually doing it in class. So that's where like you look at those other things to try to figure out which is the best way to do it. Yes.
I'm surprised that there wasn't like some sort of contingency to refer to, because like COVID is not the first global pandemic.
No, but the last one that we really had was like that was in the same level as COVID was in 1918. The world was a lot different place back then. When the Spanish flu happened, which technically didn't start in Spain, it actually started in Kansas, believe it or not. When that happened, it was a lot different world. We were actually just coming out of a world war. And that actually had a lot to do with the spread of it. So you would think we would have done all this research and had all these things in place to do it, but we're a society of we react more than we prepare. Hopefully now that we've had this experience, we start to move towards that prepare side, but don't know yet. Yes.
There's something to say too about the fact that in like 1918, the world was a very sick place. I mean, tuberculosis was.
Oh yeah, absolutely.
And now we live in a very sterile environment where
Yes.
where being sick is the outlier. We're used to being healthy.
Yes, absolutely. And that's actually, I think, this is totally my opinion, I think that's actually why COVID was so bad, is that we live in a society now, even pre-COVID, where it was a very sterile environment. We had hand sanitizer and everything else, even before COVID happened. People are using it and constantly washing your hands, doing all this stuff. It's like making sure to stay inside. Don't go outside and get dirty. Like when I was growing up, we would sit there and play in dirt. Like it's like drank out of the hose. It's like you see those stupid things. It's like, but it impacted your health because that bacteria and those things that were outside in the environment were in your body, so your body had to react to it. Now that we have so much more sterile environment, you're not exposed to a lot of that stuff anymore. So your body actually has a tendency to overreact to being sick at that point. So I think that actually caused a lot more of that issue because of that sterile environment. Yeah.
So, you like this, like the statistic with that statistic, can we, are we able to predict, because that we're being so sterile now, from COVID, that it may actually,
Weaken our system?
like a second wave of COVID, like to be.
I don't think we're gonna have a second wave of COVID because I think everybody's been pretty much exposed to it at this point. So that our bodies by design learn how to fight things very well. For the most of us, like there's people who have immunity issues and stuff like that they can't. But for the most part, our bodies fight diseases quite well. So we've survived this long. It's that whole survival of the fittest thing. If you were constantly sick, you died off. It's like, so those genes didn't pass on. So I think by being more sterile, we're limiting our immunity a little bit. And it could cause rise to other viruses and stuff that'll come out. We look back to the Native Americans and stuff that were here when the Europeans came over. Europeans brought smallpox and stuff like that with them that the Native Americans had no immunity to, and it wiped out millions of people in this country because they had no immunity to it. They never saw it before. So it's that's the type of thing that could come through. It's like when you have no immunity, and that's what happened with COVID. We had no immunity to it. It was a novel virus. Nobody had ever seen anything like it before. So there was no immunity. So you got it, you got sick. Now that it's been around and in the environment, our bodies are starting to get those what's it called?
Antibodies?
Yeah, antibodies. There's against it, so it can start to fight it on its own.
Can we use the statistics to predict like when the next pandemic could happen?
Yes and no. Most things in the world are chaotic. It's known as a chaotic system. So you can predict things to a point, but then chaos takes over. And we look at chaos as like this crazy thing, but a chaotic system is one where there's so many variables and stuff that interact with each other that we just don't have the way to model it yet. We've gotten better at it. The weather is a great example of a chaotic system. Weather is a chaotic system. There's a lot to it. We have gotten a lot better at predicting that, but even that, we're still only 3 or 4 days out to be able to predict it well. Back 10, 20 years ago, it was a day or two. So we're getting better. We have forecasts out 10, 14, a month out now. They're not accurate. So it's like if you go on your AccuWeather app and it's like it tells you that 2 weeks from now it's going to rain on Saturday, it's like you might have a 20% chance that that's accurate. So it's like it might rain, it might not. Because it's just so far out that that's what happens. And the same thing with any kind of health issues. Like we can predict a kind of spread when we know something's happening. Like monkeypox is an example that they're talking about now that's coming up. Like they're seeing where it's spreading so they can start predicting the spread patterns. But so far out, it gets more chaotic and they're not going to be able to predict it out that far. Yes?
I heard you talking about weather, so I literally chimed in mid-conversation, so I'm sorry if you said this.
That's okay.
So like when hurricanes, their paths,
Mhm.
is that like,
That's a great example of it. You know the spaghetti trails?
yeah,
That is, every one of those is a different model, is a different statistical model of where that hurricane could go. And that's why you have that cone of uncertainty. Basically, that encompasses all the different models. It's like, okay, it could be anywhere from here to here. And as you go 5 days out, that model, that cone is like 100, 200 miles wide. So those are those statistical models. And if you look at the cone, it gets down really skinny at the beginning because they can predict it a day or so out. After that, it starts to get a lot more chaotic. So great example of it. And the hurricanes are one of those ones that we're still learning about how it does it and what interacts with them. Because depending on how strong they are, they can actually push other things out of the way, in essence. Another great example of it is in the Midwest with tornadoes. We still don't know exactly. We have a general idea of what causes them, and they can start to look at how the different things in the atmosphere that could interact with them, but they still don't know. It's like, okay, what's the difference between this and this? This one sparked a tornado, this one didn't, when they basically are identical. So there's still variables that they don't have control or understanding of. That's why they can't say, okay, tornado's going to happen right here, right now, get away. Like they're almost at the point where it's like, okay, a tornado could happen. Go to your basements. It's like it might happen, it might not, but better safe than sorry at this point. So, and we don't have them as often over here. We had a few of them back. What was it? Back in April? Or no, it was Funny Girl. So it was in June. We had a couple up in the Hartford area where we had tornado warnings, and they sent out all the things to all the phones and everything else. And people were like, "We don't normally have them," so it's like we didn't understand. Like people didn't know what to do. Luckily, I don't think any actually dropped in the area, but it was that risk. So that's where you're looking at, like when we're looking at the decisions, it's like looking at how to predict things and looking at all those different options and stuff like that. And we have to understand the limitations of what we do. It's like the more computer time we get, I think artificial intelligence is going to really help a lot of this because computers are really good at solving problems in one direction. Computers aren't good at multitasking. We aren't really good at multitasking, but computers are really good at focusing on one problem and doing it. And I think artificial intelligence is going to help us to broaden that a little bit to be able to look at multiple perspectives, which up until now we haven't really had that ability in computers, and they work a lot faster than our brains do. So they can look at a lot of different options where we can't. So I think that's going to help us to be able to start to predict some more of those chaotic systems and increase our forecast models for a lot of different things. Okay. All right. Here's two graphs. What can you tell me about the upper left graph?
Data is inconsistent.
Okay. What's the general trend?
Upward, but it kind of like levels out a little bit.
Okay. So the number of late deliveries is increasing. Okay. What about the bottom left or bottom right graph? Okay. So for those in healthcare, is that a good thing? No, the person's getting sick. Their temperature's going up. That's a problem. I also showed these graphs for another reason. The bottom graph is right. The top graph is wrong. So when we have a tendency to, whenever we make a graph, we like to connect things. Okay. We like this because we like things that are connected and it looks nice. However, not everything should be connected. When you draw a line, the line has meaning. Okay. That line means the data between those 2 points generally exists. So when we took the patient's temperature history from 6, 7, 8, 9, those hours, and it went from 99.5 to 99.6 between 6 and 7. At some point between 6 and 7, it went through all the other numbers between those two numbers, right? It didn't jump from one to directly to the next one. It has to actually travel between those points. And from 7 to 8, it went from 99.6 to 100.1. So again, it went through all those values. All right. So that line makes sense. Yes.
Would that, the first graph on the left, should that be a different type of graph, like a bar graph or something?
It doesn't necessarily have to be a bar graph. Bar graph would be fine. It could be just a dot plot. You could just put the dots because it says late deliveries each week. We're tracking how many deliveries were late each week. So in week 1, there was 7 deliveries late. In week 2, there was 9 deliveries late. There's no information between week 1 and week 2 to say that there was 8 deliveries late. 8 has no meaning in this situation. So that line doesn't have meaning and shouldn't be there. It should just be the dots. Okay. Like I said, and I guarantee you, you've all done it at one point. Your teacher told you to draw a bunch of dots and you connected all the dots. Be careful with that. Okay. Yes, this is a graph that you probably could have done as a bar chart. It would probably have been a lot nicer than just doing the dots on it. But a dot plot's fine. A scatter plot is totally acceptable. They don't always have to be connected, though. And you get the exact same information. So like if you looked at just these dots, like you don't necessarily need the lines. I'm going to erase the lines in a second. You don't necessarily need the lines between them to get a general idea of what's happening with the data. You can still see it's going in an upward pattern. You can still see, well, it's kind of leveling off, but it's still, like if we drew a line here, it still has a tendency, it's still on that upward trajectory. Even though it's oscillating up here, it's still, the points on either side are still getting higher. Okay. So just be careful when you're making your graphs. We're going to talk a lot more about that in chapter 3, but they put these two graphs in there and they didn't even talk about the concept that it was lined and it shouldn't have been. So I wanted to bring that up. All right. Let's figure out how we're going to collect data. You have 2 different ways we can collect data. We can collect data observationally, and we can collect data in terms of being a controlled experiment. What are some examples of observational data? Yeah.
If you're outside with a student, different species that gives you like a bird feeder or something.
Okay. Yep.
Someone walking through the classroom and counting over the course of the class how many people raise their hand, how many don't.
Yep. So observational data is just that. You're observing information. Okay. You're observing what's going on. You don't have control over it. You didn't set it up. So That's just an observational data. A controlled experiment is when you designed everything that's going into it. Okay. So when you were in high school, because this typically doesn't ever happen in college, remember when the principal or admin used to come into the classroom and sit in the back and watch the teacher? Okay. So now in most situations, you'd think that would be observational. And in most situations, it was. See, the principal's in the back observing what's going on. I always like to call those controlled experiments because I would make sure my class had I knew ahead of time they were coming in, and I made sure I picked the right class. I made sure I picked the right lesson. I made sure I told the kids that it was going to happen. I controlled absolutely everything possible that I could about that situation to make sure that it worked out fine. Until I didn't care anymore. And then I didn't care what they were doing. But you do that. And I guarantee at some point you had a teacher that would say, okay, if your class is good, we're going to have a movie time or something on Friday, or like I'll bring in pizza or something for the class. Like people do that all the time. Okay. So while technically it's not a controlled experiment, we tried to control as much of those variables as possible. All right. Most of your controlled experiments are your actual scientific studies that are going out and doing. So they're going to organize it. They're going to say, okay, these are the things I'm going to be looking at. I'm going to set up. Actually, is it the next slide? It's not. So we're going to get there in a second. We have to do a couple other things. I might actually show you an example. All right. So whenever we're setting up an experiment, controlled or observational, there's two different variables that we're looking at. Our response variable and our explanatory variable. So the response variable is what is our interest of the study. This is the measures of our information. The explanatory variable is what we think caused those changes. Remember, it's always going to be a change. If we're not noticing a change, then we didn't do the experiment correctly, or what we're trying isn't working. We need to try something else. There's always got to be some kind of a change. So response is what we're looking for, and the explanatory is why that is happening. All right. Now that we have this. So I want to study tomatoes. Really? Since my screen's not going to switch. So I have a new species of tomato that's been genetically engineered to increase yields. All right. We all know the horrors of genetic engineering, right? It's horrible. We should never genetic engineer anything. Well, unfortunately, I hate to tell you, everything you eat's been genetically engineered. The reason why we have as much corn as we have today is because it's been genetically engineered to grow better and to grow longer and to grow faster. If we didn't do this, we would not have enough food on this planet today to eat for everybody that's around. Okay, so while we hear right now that whole like the GMOs and that movement and everything else has that negative connotation to it, it's been this way for almost a century now. Actually, even before that point. It wasn't necessarily done in a lab. It was done through selective breeding. So if any of you own a dog, most dogs that you have today is a product of selective breeding. All right. Dogs were bred for certain jobs. And as crazy as this is going to sound, I have 2 corgis, and they were bred to herd cattle. Told you it's going to sound crazy. They were literally bred to herd cows. These little dogs with short little legs. Big cow. So that's why corgis don't have tails. Because they bred them because the cows would bite the tails. So they started breeding them so they didn't have a tail. So they found ones that didn't have the tails and they bred them that way. So this way they couldn't bite the tails. Yes?
Why don't they just use a sheepdog?
So different type of animal.
Yeah, but a cow can run pretty fast as well.
Not nearly as fast as a sheep. And corgis can actually run really quickly. Don't think they can run real quickly. But it was it also came up with the term ankle biter. The corgis would bark and nip at the ankles of the cows. That's where the term ankle biter came from for the short little tiny dogs, because that's what they would do. But they would bark and they would nip, and that's what got the cows to go the directions they were supposed to be going. But through selective breeding, that's how they got their tails cut. That's how the tails became basically nubs, so they don't have a tail anymore, because they would do that so the cows didn't bite them. Sheepdogs were the same concept. They were bred to be very loud in their barks because they were trying to herd sheep in large areas. So they weren't actually chasing after the sheep, they were running around the sheep. So your Australian shepherds and those type of things, and the sheepdogs and stuff were designed to be a lot leaner and faster, to be able to run around to herd those large sheep that were out in the mountains and in the fields. So you have your bloodhounds and stuff that were bred specifically to get a better sense of smell, so they can smell a lot of different things. And now they can actually, they have some dogs that, as I don't quite understand how it does, can smell cancer in people. It's like, those are the types of things that they're done. Food was done the exact same way. It's not done the same way in terms of how they're bred, but when they're, and I know very little about food and how it's done, but when they actually bred them, which it happens, they did specific styles to get a faster yield or to get larger crops and to get them to grow quicker. So this way they have more food for sale. They also bred them so that the ground, because when you grow certain plants in the ground, it sucks out certain nutrients. You can't use that same ground again for that same plant, so you have to rotate it. So they started genetically engineering them so that you can keep planting them in the same spot, and it doesn't pull that minerals out of the ground, so it actually still is healthy for it. So we've seen this quite often. Now it's being more done in the lab, which is what people have issues with. So how would you set up a study to determine if your new species of tomato produced higher yields? So, okay, we'll take a step back. What's the experiment? What's the two variables? What's the response variable? What am I measuring for?
Tomato yields.
Tomato yields. That's what I'm looking at. Okay. And what would be my explanatory variable? Yeah, the genetically engineered species that is. So I would expect that one to give me a higher yield, right? Okay. So we've got those two. Great. What are some of the variables? So if I'm going to do a controlled experiment, what are some of the variables that I have to take into account? Yes. Yep. Okay. So yeah, rain, sunshine, the types of soil, those type of things I'd have to look at, right? So those would be the confounding variables if I didn't take care of them. So how would I set up an experiment where I can control those? Yeah.
Greenhouse.
Greenhouse? One greenhouse or multiple greenhouses? One. Because if you have multiple ones, how are you going to keep all the greenhouses exactly the same? Yeah.
We need a big.
Yeah.
thing you have to keep track of is the amount of dirt that you use for each plant, if it's in like, if it's just in the ground versus a pot.
Yep. So one of the options that we have is you basically can take and you set up your plot so that everything's identical. So a greenhouse is a great way to do it, because in the greenhouse you can control at least the rain, the actual waterfall that's in it. And because it's not actually in the ground, we can control the actual exact soil composition and everything else among it, so we can control that. And because it's in the same spot and it's in one greenhouse, we can control the sun because it's all going to be the same for across the things. It might not be, we might not know how much sun's going to get, but they're all getting the exact same amount at the exact same time. So that's also important. So we can start to look at how we can control those variables. That's why it's important to think about those variables. Because if you don't think about them ahead of time, then they become confounding variables that can cause you problems in your results. Okay. So that's some of the stuff that you have to think about when you're trying to create that controlled experiment. Okay. How would I do a study for an SAT prep class? If I wanted to do an SAT prep class and I wanted to figure out if it's helping you improve on the SATs. Yeah.
You would just maybe have set up like two groups of students. I can do it for like a group around the same maybe the GPA level, maybe or at least like beginning like understanding, and then have one group like not use the class and the other group use the class, and then you can see if they improve the grade.
Okay. You're getting there. You're getting close when you said, okay, well, I have to, because one of the problems with using two groups of people have a lot of variables. So you have to kind of make the two groups as close to as the same as possible, which might be kind of difficult with people.
Feels like too broad of a thing because like even you can go bare minimums, like some people are bad test takers. And so then like they'll be like good as well.
Okay. So how, because this happens a lot, like whenever we're bringing in a new program or something, that we have to have some kind of data to say it doesn't work. Okay. So it's like there has to be a way to do this and still somehow get that controlled setting. Yeah.
You do the same class, but over like multiple years, so it's different groups of people within the same framework.
That's what the state does.
Yeah.
If you take it, so you guys are too young probably to remember we had CAP testing, and then we had smarter balance testing, and now they just use the SATs. But that's actually what the state does. They use the data from 1 year group of students, so the juniors from last year compared to the juniors of this year, to determine if the changes have made any difference. However, this is one of the things that the teachers always complained about. It's comparing apples to oranges. They're different groups of students. So where you were talking about isn't too broad, it's like because there's a lot of students that are bad test takers, or there's students that take this just don't care. It's like, why am I taking this? I just don't care. Like I might be a smart student, but it makes no difference to me. Okay. So is there a way to do this where we can minimize those variables as much as possible?
And maybe like if there's two groups, you can do like the same people, like have them take the test before the prep class and have their grades, and then have them do the improved, like, the preparation course. Is that like?
That's typically how this is done. When you're trying to determine if a thing works to improve the SAT performance, you do a test. You do the test beforehand, have them take the SATs, get their scores, have them go through the prep class, take the SATs, get their scores. And what you want to do is you want to show improvement with that group, but you want to show that that group's performance would be better than a typical performance. Because if you take the SATs and you take it again, you're always going to improve your score. On average, it's about 100 points that you improve your score just by taking the SATs a second time. So you want to show that the prep class is significantly higher than the standard change. But that's data that we would have. And that would eliminate a lot of those variables, like, is the student a bad test taker and stuff like that? Because even if they were a bad test taker, they would have bombed the first test, and they're going to bomb the second test, but probably not as bad as they bombed it the first time. So it's like, it's that type of concept in there. So you're comparing the same, it's known as a longitudinal study, where you're taking the same group of people and studying them multiple times to see what the changes and stuff. Good. All right. Everybody heard the placebo? Okay, typically if you're in a drug trial, it's going to be a sugar pill. Why do we need to have a placebo?
I guess human mind is very powerful when it comes to like influence.
Yes. It's known as the placebo effect. Even if what you're doing has no actual impact on the outcome, if you think it does, it will. Okay, so when you're doing a study, you always typically are going to have some kind of control group. Now, you can't just have the control group. The control group can't know they're the control group. Okay, they have to think they're just getting the drug as everything else. So that's where the placebo comes into effect. You want to see that the actual drug does better than the control group. And that's where I was talking about the SATs, where your normal group, that's like your control group, that's your placebo. They're doing the same thing they always do, no matter what. They're going to take the test. I want my experiment group, the ones that are taking the actual whatever whatever response, that variable that I'm looking at, they're doing that. I want them to do even better than the control group. Okay, so that's also how they figure out a lot of times the side effects. If the actual experiment group has a certain side effects that are extreme, that are more than the control group does, you would say that actually has some impact with the actual vaccine or medicine or whatever else it is, and that has to go in the actual list of possible side effects that could occur. And if you've ever read one of those little pamphlets with all the side effects, you will never take a drug again in your life, because every possible side effect is on there, including up into death on every one of them. So the placebo's there to monitor that and to get a little more control over it. Yeah.
But, I could be wrong, but don't companies just do that just to target it behind? Just so they.
Yes and no. Yes, they do that, but even if you have that effect and it's directly caused back, they're still going to be on the hook for some of it. But they have to have the scientific data to show that that happened. So they can't just say you could die from this unless somebody actually died at some point during their trials. But so yes.
Why they say you or someone you know has died, then
Yeah.
Oh, wow.
The other thing is that when you look at the side effects is everything. So like when you're doing experiments with people have a lot of issues coming into it. And a lot of times you're using these drugs on people who are sick. Like that's the entire purpose of the drug, is to help somebody get better. So these are people who could die for other reasons, but since they died in that group, it has to be listed. Okay, so if you're studying a cancer treatment, for example, and the person dies of cancer, but they died while taking your treatment, you don't know if they died because of your treatment or if they died because of the cancer. There's no way to determine that. So you have to say a possible side effect of this is death because that happened. So, but yeah. And everything, like even any medication take over the counter, it's like you take too much of it, it can kill you. Like you can take too much ibuprofen and it'll kill you. So they have to put that because there is a possibility, because they don't know how stupid you are. So it's like, and that's where the lawyers are going to do things afterwards. Like, well, they took a whole bottle of it. Of course they're going to die. It's like, it wasn't the drug's fault, those type of things. So yes, they do it to cover their butts to a point, but they do have to have some reasoning behind it. But that's why you'll see like a list of things like headaches, nausea, diarrhea, those type of things on all of them. Because at some point, somebody probably had this during it, but they had food poisoning because they went out for bought sushi or something the day before. It's like those little things. So that's why. All right. Talking about migraines. So London scientists conducted a study to determine if chocolate can trigger migraines. I had a friend of mine whose daughter got migraines, and they ended up figuring out that it was red number 5 that caused her migraines. They figured this out because of Skittles. they figured out that every time she ate Skittles, she would get a migraine. And then if she ate M&M's, she'd get a migraine. And it was like they were trying to figure out the connections. And what the doctor said is, okay, let's split them up. And it was only when they ate the red ones that they got migraines. It ended up being the red number 5 that was in it that would trigger her migraines. So there's a variety of things that could trigger migraines. So 12 migraine-prone suspects were given a peppermint-laced chocolate candy, and 8 migraine-prone suspects were given a peppermint-laced placebo made of a bunch of other crap, not chocolate. 5 subjects from the group were given chocolate, developed a migraine headache within 1 day, and no one from the given placebo group developed a migraine in the same period. All right. Which phase of the scientific method best describes the study? So which stage were they at in that scientific method? Yes,
The experimentation.
they were experimenting. This was an experiment. They were determining that would be the hypothesis. They said that chocolate's going to trigger migraines. Then they did an experiment. So they were at that point. Is this an observational study or a controlled experiment? This is controlled. They've got a control. They've got the placebo group there. They've got their subjects. What's the response variable? Huh?
That would be the result.
No. The response variable is what you're studying. The chocolate is my response variable. Yeah, it sounds weird. Totally. And that's why we go through this, because like response, okay, that's what happened, right? No.
Let me get this clear. So the response variable is what we're studying.
Correct.
Okay.
Yes, the response variable is what you're studying. The explanatory variable is what happened. So in this case, the explanatory variable is a migraine. Yes.
Response variable because it's like causing the response.
Yeah, you can say it. You can think about it that way. So the response variable in this case is the chocolate. The explanatory is a migraine. Which group's the treatment group? Yeah, the ones that were given the peppermint laced chocolate. The control group was the ones who were given the peppermint laced non-chocolate. But it had to look the same. So in essence, they were given the peppermint patties. All right, good. Okay. All right. Of everything we talked about so far, this is probably going to be the most confusing part. And I guarantee it's going to be the most confusing part when you take it in Hawks. It's how we identify data. A bunch of different names for it. The first couple that we're going to look at is what's discrete and continuous. Okay. So, discrete types of data is where it's very specific information and there's nothing between them. Okay. So, give me an example of a discrete piece of data that would relate to you or relate to general people in general. Yeah.
What kind of car are you driving?
Yep. So, very important piece of information. Discrete data does not have to be numerical. Okay. So that's important to understand. Discrete does not have to be numerical. It just has to be very specific information with nothing between them. Now, can you give me an example of a discrete piece of data that is numerical that relates to a person? So let's say your blood pressure is 120 over 80. And the next day your blood pressure is 130 over 92. Was there anything in between the 120 over 80 and the 130 over 92? Yes. So that would be continuous. Because the data between those does exist. Even though you didn't measure it, it does exist. Do you only age on your birthday? No. Yeah. Huh? Well, I didn't hear what you said. That's okay.
I'm like confused, so is that like, is like, when we mark the value, is that kind of how you mark your birthday? As like, is that what you do?
So yeah, so the question was, okay, so is age continuous or discrete? Right, because you constantly age. You don't just age on your birthday. You constantly age, even though you don't necessarily write down your, unless your mother still counts by months, which I don't understand why after like 12 months people use months, but it's like that's the type of thing. Even at that point, it's still continuous. You're still aging every single day, every single second. You're still aging. Yeah,
Name, like the name of the car, right, would be.
that's discrete. Yeah.
And then the year of the car.
Okay, we're still sticking with cars apparently. But yes, but the year of the car would still be discrete because you have a 1999 car, a 2020 car. Those, yeah, you don't have a June 2020 car. You have a 2020. Yeah, so that still would be discrete. So can nobody come up with one that has to do with you? Yes. That's not numerical though.
How many meals you eat a day?
Okay. It's really hard. So it's really hard to come up with something that's discrete, numerical that comes up with a person. Yes.
A specific day of your birth. That is numerical, and that would be because it's not changing.
Correct. Okay. That'd be, I'll give you that one. Weight is continuous. Yes. Yep. Good.
Did you do like if somebody wakes up like the same time every day?
You can do the time of day you woke up. Yeah.
Number of birthmarks.
Yeah, I was gonna. That's how I was gonna go. I was gonna go the number of piercings. Like those are the types of things that those are discrete. There's very specific values. You can't have 1.5 piercings. It's 1 piercing or 2 piercings or 3 piercings. Those type of things. So, so when I look at it, that's typically how I look at it. Is can I have a half of something? If you say yes, therefore it's continuous. If you say no, it's discrete. So can I be 3.5 years old? Yes. Therefore, age is continuous. Can I have a 4.5 shoe size? Yes. It's continuous. But you look at it, it's like, okay, so that the size of your foot is continuous. Shoe size is discrete. Because while there's a 4.5, there's not a 4.25. There's a 7, there's an 8, there's a 9. There's typically not those breakdown of all of them. So shoe sizes typically are discrete, where your size of your foot is continuous. That makes sense? Yes.
Is it true too that something that's continuous is liable to change in some way? So your shoe size cannot change. That is set at whatever it is, but the size of your foot can change.
Well, no, your shoe size can change. This is why you have to buy new shoes all the time. Your shoe size changes. Even as you get older, your shoe size can change a little bit.
So the shoe itself, it cannot change size.
Oh, right. Yes. Yeah. Yeah. Okay. I got what you're saying now. Totally got what you're saying now. Yes, the shoe cannot change. So yeah, be a good way to think about it as well. There was one other one I was going to come up with, and I can't remember what it was. Before we got into the shoe thing again. I don't know. It'll come to me in a minute when I'm not actually talking about this. All right. So continuous is data that can take any spot inside that range. Okay. So you'll have halves, you'll have quarters, it's basically every value goes between it. So when you're going from 1 to 2, it's got to cross between all those things in between it. So now think back to the chart, the graphs that I showed you before. That's the difference between the two graphs. The graph in the upper part where I said we shouldn't have lines, that was discrete data. The data was very specific points. The temperature on the bottom was continuous data. The values between those points had some information, some meaning. Okay? So when you have continuous data, the lines make sense. When you have discrete data, the lines don't make sense. So understanding what type of data you have is going to have an impact on the types of graphs that we're going to use next class. All right. This is the hard one. Level of measurement. So level of measurement is the quality of the data as is referred to. So this is the type of data. These quality is not as is it good or bad, it's the type of data. So we describe it as nominal, ordinal, interval, or ratio. We're going to look at all four of these. So nominal, ordinal, interval, and ratio are the four levels of measurement. And I will tell you the homework for Hawks, this is going to be the hardest one because you're going to have to try to figure out which each of these types are on it. So all right. Nominal data. Nominal data is ones that is a variable possesses a character or is a characteristic. Okay, so it just doesn't have that characteristic. So we're talking about the type of car. That's nominal data. If we're talking about the color of a car, that's nominal data. Okay. Yes.
So like, could a name be nominal data?
Yes.
Because nomen, that's Latin for name. So
Yes.
no-
Yep. Yep. So if you're thinking about it, like when we're talking about this stuff, is yes, there's a possibility of it being numerical, but most of your data that's non-numerical will fall into that nominal data category. Right? It is a data point. Right? The most important piece to it is you cannot do any calculations on it. All right, so nominal data, you cannot calculate. You can't add them together. You can't divide them. You can't multiply them. There's no point to that. Okay. The other thing you can't do is you can't put it in order. Okay. So you have a Toyota, a Honda, a Ford, a Chevy. Putting them in order makes no difference. I can put them in alphabetical order, but that doesn't matter. It's not impacting the actual data that I put them in alphabetical order. If I took all of your names, okay, that's all nominal data. Even if I put them in alphabetical order, there's no meaning behind the alphabetical order, except I just put them in that order to make it help me. Okay. So that's the key to nominal data. Ordinal data, the only difference with this one is, what's the root word for ordinal? Order. I can put the data in order. Okay. So we're talking, let's keep with the cars because you guys liked the cars before. The year of the car, that is ordinal data because I can put those in order. And that order has some meaning because it tells me the age of the car. Okay. So ordinal data I can put in order. All right. Where do that? Heights. If I took everybody's height in here and I put those in order, that would have some meaning. But it's ordinal data because, again, the big piece to this, so the difference between these and the next one we're going to talk about is adding and subtracting them wouldn't have any meaning. All right. If I took all your heights and put them in order, me subtracting your heights, that doesn't have any real meaning or information it's going to give. Okay. So a lot of times when you see ordinal data, it's going to be something like this. Where you have rankings. Star ratings, again, is ordinal data because I can put that stuff in order. But again, if I added up 5 bad reviews, if 5 people gave them 1 star, does that mean they were good? Because now they have 5 stars? No, right? That would make any sense. So if 5 people gave them 1 star, that doesn't mean they have 5 stars. They have 5 1-star reviews. So putting them together doesn't mean anything. But putting them in order does. That make sense? Yes.
But that doesn't, apply to like the median.
No, we're not even there yet. We'll get there next class. So yeah, so you can't, so there's certain types of data I can do certain things with. When we're looking at the mode, the median, the mean, and stuff like that. Certain types of data I can do those with, certain types of data I cannot. Nominal data, I cannot do any of those calculations with. Ordinal data, I can do some calculations with, and some information with. The next two, we're going to be able to even do more. Next one, intervals. So I probably shouldn't have given the height example in the last problem in the ordinal data because height actually is interval. Because I could subtract your heights and tell how much taller you are from each other. Okay, so interval data is where the difference has meaning. So the space in between it has some kind of meaning. So if I subtracted those, that information gives me some information about it. Okay, so if I took the smallest person and the tallest person here and subtracted them, I could figure out the differences in heights. That would give me some information. I could technically do that with the years of cars too, to figure out age difference, but yes.
Would this be considered numeric? The other two,
Yes. So interval has to be numeric. Yes. The other two, ordinal and nominal, you do not necessarily have to be numeric. So I can put things that are non-numerical in order and it will still have meaning, like stars and stuff like that. But even stars have some numerical value to them. But I can order things that aren't numeric. Interval has to be numeric because I have to be able to do calculations on it. So if I'm looking, the example they gave was temperatures. So if we're looking at temperature differences over the day, so 3 degrees makes sense. It's like the change in the temperature was 3 degrees. That has meaning to it. Now, obviously, there's no way to subtract names. There's no way to add names, stuff like that. So these have to be numerical values. The last one is ratio. So ratio is very similar to interval, so we can still do all our calculations on it. However, it has a meaningful zero. So a meaningful zero means that you can actually have a value of zero, and that can be used. All right. So if we're looking at height, for example, if you were 0 inches tall, there's no height, right? Distance can start at 0. That's fine. Weights can start at 0. That's fine. Trying to think of something that wouldn't be easy. Like the last one we're looking at, temperature. It has a 0, but the 0 is just like any other number. Yes. Yeah, you could definitely do that. So ratio typically ends up being ones that you can, so in intervals we can add, subtract those. Ratios, you can do the multiplication and divisions, and they have some meaning to it. So the example that they gave is this. And this is why I said these are hard once you start looking at them because like they're close sometimes. So a ratio, if I'm looking at your friend had $40, you had $20, you have twice as much money. I can divide those, that twice as much money has meaning. There's information behind it. So, and I can only do division, stuff like that, if there's a 0 that means something. Like temperature, dividing it wouldn't make any sense. Okay, so that's why that one more falls towards that interval aspect than the ratio aspect. All right. Qualitative and quantitative. Yes, they use two keywords just to screw with you. But this goes back to the exact question that was asked earlier. Does interval have to be numerical? Qualitative can be anything. Qualitative is qualities of the object. Does not necessarily have to be numerical. It can be, doesn't have to be. Quantitative has to be numerical. So your qualitative data is your nominal and ordinal data. Quantitative is interval and ratio because they're quantities. So qualitative is a quality. Quantitative is a quantity. It's a numerical value. Don't think I did this will be a problem. All right. Actually, I'm gonna do a different one. Hold on. I'll do this one. All right. For each of these, tell me if it's, write it down. Nominal, ordinal, interval, or ratio. All right. The time it takes for a student to complete an exam.
The interval.
Why?
Because it's numeric, but it's not like you can't feasibly have a zero. I mean, you technically could, but it wouldn't be a physical. You wouldn't then they wouldn't have taken the exam period.
Okay. Can I say somebody took twice as long as you to complete the exam? Yes? Then it's ratio. Because if I could do that, then I can divide them. And if I can divide them, it's ratio. So don't get stuck up on the meaningful zero one there, because that's really hard to understand. Think about it as, does twice as much of this mean something?
Oh.
Okay, it's an easier way to figure it out. Think about it. Majors of randomly selected students in the university. It's nominal. Why?
Because it's just names. And
Yeah,
it-
it's
it
just a bunch
doesn't
of
matter
names.
What the order is, or
Correct.
it's just a characteristic of what it is.
Yeah, putting them in order doesn't mean anything. The categories which best describes a person how they eat chocolate: frequently, occasionally, seldom, or never. Order. Because I can put them in order. I can put all the people who never eat chocolate in one category and label out. For people who never eat chocolate, I don't know what's wrong with you, but okay, we'll let it be. The number of pounds of snack food eaten by an individual in his or her lifetime. Ratio. Because I could say somebody ate twice as much as somebody else. All right. Chapter 2 is done. So you should be able to do chapter 1 and chapter 2's homework in Hawks. Also, again, make sure you're set up in Hawks. Before Wednesday's class, I need everybody signed into Hawks and set up. Okay? Because I guarantee I'm going to get asked that question probably by the end of the week. So, and I don't want to mark anybody not here because they didn't do what they're supposed to do.